Okay, so this talk, Beyond Infinity, is about Hilbert's Hotel, which is an infinite hotel. And since you can't really have infinite hotels, that means you have to take what I'm saying with a pinch of salt, but there is some serious mathematics behind it. The serious mathematics behind it is due to David Hilbert and Georg Cantor, two great mathematicians, rather different mathematicians. Cantor was the man who discovered that there's more than one kind of infinity. So until Cantor, people thought that sets had either finitely many points in or else they were infinite, and that was it. But Cantor thought there are different sizes of infinity, and he proved it. And so some infinities are bigger than others. And Hilbert was a great supporter of Cantor, and he had his own little arguments involving infinity, which were known as the paradox of the Hilbert's Hotel. Now, it's not really a paradox, so nothing I'm going to talk about is really a paradox. It just illustrates some of the mathematics involved in infinity in a slightly informal way. So this is about Hilbert's Hotel, and we'll call the hotel manager Dave, since it's David Hilbert, and how he has to deal with the fact that there's almost always a person in every room, and yet there are still more people trying to get into the hotel. So most hotels have only got a few rooms in. Here's one with 5. It's beginning to fill up. Now it's full, and the next person's a bit unlucky. So can't get in. That's the story of a finite hotel. Whenever a room's full, you can't take anybody else in. But it's different if you've got an infinite hotel. So here's Hilbert's Hotel. It's got infinitely many rooms, but every room has got a number on the door. 1, 2, 3, 4. That's easy enough. I guess for the really big million-digit numbers, you have to write fairly small. But every room's got a number on the door. There's no room infinity. There's only rooms 1, 2, 3, 4, and so on, which makes infinitely many rooms, each one with some particular finite number on its door. Of course, I can't fit them all on the screen, so you have to imagine that rooms 8, 9, and 10, and so on are all off to the right somewhere. And you've got some suitable, infinitely fast means of transport to get you to the room you're supposed to get to, and all these other things that you can't really do in practice. Okay, but it's a very popular hotel, and sometimes every room has a guest. That means infinitely many people, but, well, let's assume you can have infinitely many people. One guest in each room. And now what's Dave going to do when one more person turns up? Well, there's room for one more, as we will see, because Dave said to the new guest, it's no problem, we'll fit you in, just a minor inconvenience for everyone, we'll just make everybody move to the next room along. They all move simultaneously, really, because otherwise it's going to take too long. But each person moves one room to the right, so the person in room 7 will move to the room 8, and room 6 will move to room 7. Let's see where they're going. So person in room 7's gone off screen to the right. Room 6 moves to room 7, and so on. That leaves room for one more. Now you may say that's cheating. What happened to the person in room infinity? There isn't a room infinity. There's only one room for every finite number, and that means there's always one room further to the right. And that room is empty because that person moved one room to the right. So no problem. Okay, that was easy. Problem is that next week, or a few days later, a bus turned up which had got infinitely many passengers on. The passengers were numbered 1, 2, 3, 4. And Dave thought for a moment, well, could try moving everybody one to the right, I can fit one in, move everybody to the right again, fit another one in. But I'll never get anywhere that way because I'll only ever get finitely many in. Let's see how you get infinitely many people in. I know. he asked everybody to double their room number. So some people are going to have to go off screen. Person in room 4, 5, 6, and 7 here are going to go off screen to the right somewhere because they're going to rooms 8, 10, 12, and 14. So then we've got to move the other ones, room 3 to room 6, room 2 moves to room 4, and room 1 goes to room 2. And now we've got some rooms left. In fact, we've got rooms 1, 3, 5, 7, 9, and so on left, and that's plenty of room to fit infinitely many people into. And in they go, as you can see. We put the first new guest in room 1, second new guest in room 3, third new guest in room 5, and we fitted in infinitely many guests. No problem at all. Things got a bit harder for Dave after this, but he's very clever, so he's going to manage okay. So a week later, a bus turned up with passengers whose shirts were labelled with positive fractions in their lowest terms. So there they are. There are a few of the passengers, 1 over 2, 11 over 6, 3 over 1,000, and some with some very, very big numbers on top and bottom, which had to be written in very small print. Dave had to think about it and came up with a solution. Actually, he thought up 2 different solutions. One of them is on your printed handout, and the other one is going to be on the screen. So he started by freeing up rooms 1, 3, 5, and 7, just as he'd done before, by asking everybody to go into the room twice the room they started in. So that freed up infinitely many rooms, but those rooms it's not obvious how to fit the new guests into. Now, on your printed handout, they moved into the room 2 to the m times 3 to the n minus 1, just in order to make sure it was an odd number. But this time, just to avoid the minus 1, we'll do it with 3 to the m, 5 to the n, because that's already an odd number. And because 3 and 5 are prime, all of those numbers are different. If you change either m or n, you always get a different number. So they all end up in different rooms, which is a good thing, because otherwise they might complain. And so you manage to get them all in, and you've even got infinitely many rooms spare, if you think about it. But it's such a popular hotel, they fill up pretty quickly anyway. So a week later, when I say the hotel is full, what I really mean is that every room has a guest in it, because as we know, this hotel is never full. Infinitely many buses turned up the next week, and the buses are numbered 1, 2, 3, 4, and they've all got infinitely many passengers on. So I have to tell you what sort of a T-shirt the passenger from the nth bus and the nth passenger on the nth bus was wearing. Well, just wore a T-shirt with this easy symbol, M, N. And Dave knew how to deal with this straight away, because he'd already figured out how to deal with the fractions. Freed up the rooms as usual, rooms 1, 3, 5, and 7. And then he put the nth passenger from the nth room, the nth passenger from the nth bus, into room 3 to the m, 5 to the n. This time he did at least fill up all of the 3 to the m, 5 to the n's, though it still leaves plenty of other odd numbers free. So I've said that the hotel can never be full, but it still may not be able to cope.